just going to try something on the calculator here. F of x equals sine x, and what I'm going to do is diff sine x. It's cosine x. Why? Well, what we're going to do today is look at derivatives of circular functions, and what you can see here on the graph, this solid blue graph, is f of x equals sine x. And if you note the graph here, we've got a zero gradient point here, a zero gradient point here. So what if I had a gradient graph? There would be a value of the gradient as 0 there and 0 there. Okay, so this dotted line here represents f dash x, the first derivative of f of x equals sine x. Now, what we also note is that we've got a positive gradient here, getting closer and closer to a zero gradient. And so what we have over here is a positive gradient. So positive gradient getting closer and closer to a value of 0. Now what we find is that we've got a negative gradient from here all the way down to here. So what should happen with my dotted graph is it should be negative. Now what's going to happen though is it goes negative and then it switches back to a zero gradient. So it goes negative, 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 but at some point it has to get back to 0, so it cuts back to 0. What happens from here is we've got a positive gradient again, so our graph goes positive. And what it will do, because it's a circular function, this process will just get repeated over and over again. Now, if you have a look at this function here that's being graphed, I'll just try to draw it in a different color so it makes it a little bit more obvious and maybe even increase my pen thickness. Here we go. So this graph here, that's the gradient graph, and if you note what happens, that's pi on 2, that's pi, that's 3 pi on 2, and ultimately finishes at 2 pi. So if you look at that segment of the graph only, hopefully you recognize that that's just y equals cosine x, okay? And so that's why if we derive y equals sine x, what we get is dy dx equals cosine x, right? Now, going back to my original pen thickness, how do I do that? I stay in red just for something different. So if you think that f dash x looks a lot like cosine x, then you are right. Thus, if f of x equals sine x, f dash x equals cosine x. What if it's got some k value there, dilation from the y-axis? Well, we can actually use the chain rule to do that. So if my function is f of x equals sine of kx, then what I'm going to do is say that y equals the sine of u, where u equals kx. I'm going to make that u substitution. Now remember that what we do is dy du. We already know that the derivative of sine of x or sine of u is equal to cosine of u, and du dx over here is equal to that, which is k. So what we're going to do then is multiply these two together and make the u substitution. So we're going to say that f dash x equals k multiplied by cosine with u substitution, where u is kx. And there's our derivative, okay? And that actually is on the formula sheet. So here it is on the formula sheet. It's not magic. It's not mathematicians giving you something that you shouldn't know how to do already. That's just the chain rule. Okay, so you don't need that rule. It's nice that they give it to you, but in a way, I sort of feel like I wish they didn't, because really all it requires you to understand is the chain rule. All right, now what we've got again is cosine graphed here. So this solid graph represents cosine in this case. And what I've got underneath it, or not underneath it, but the dotted line there, is the graph of its first derivative. All right, so note here that we've got a zero gradient point here. So we start with a zero gradient point. And what cosine does is it has a negative gradient to begin with, all the way down to this stationary point here. So here's the second stationary point, zero gradient. And what it does is it's got a negative gradient all the way through, negative gradient all the way through, with a comeback point where it decides that I'm going to go negative, 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 more negative. But then at some point here, which is actually this point here, it goes, all right, got to get back to 0. So it starts cutting back towards 0. Okay, and notice here that cosine goes positive gradient all the way to this point. So notice from here in, we've got a positive gradient and it does the same thing. It goes, I've got to get back to 0 now. So it goes back down towards 0. So let's have a look at the one segment of it from 0 to 2 pi. And you notice that that looks scarily like sine, albeit reflected in the x-axis. So it looks like y equals negative sine x. And if you think like f dash x looks a lot like negative sine x, you are right. Thus, if f of x equals cosine x, f dash x equals negative sine x. And the same approach here to derive the rule for differentiation, where what if f of x equals cosine kx? That is, there's some form of dilation in the y-axis. Well, again, let's just bang it out using the chain rule. I'm going to say that if f of x equals cosine of kx, what I'm going to note is y equals the cosine of u, where u is equal to kx. dy du over here is equal to, now the derivative of cosine of x or cosine of u we just saw above is negative sine of u, and du dx in this case is equal to k. Multiply those two together and we're going to say that f dash x equals k, or let's put the negative sign in, negative k sine of u, let's make the u sub at the same time, kx. Negative k sine kx. Let's see how that marries up with the one on the formula sheet. If d dx, if I'm differentiating cosine ax, the result will be negative a sine ax. Girls, I've got a confession to make. I never remember which one is the negative version of it, and I do consult my formula sheet quite often on that. Okay, if you force me to, I could graph them to work it out, but I do consult my formula sheet quite often. So I'd advise you to have this in front of you on your desk or whatever it is, and access it frequently. All right, let's try out some. Oh no, sorry, I've got to do tan. So what about f of x equals tan x? Much more complicated, and a proof is beyond the scope of the course. And to be completely honest, I don't think I can do the proof anyway. So we're going to say that that's beyond the scope of the course. It's not intended to be part of the course. And so let's just have a look at what happens. F of x equals tan x and f dash x are below. So this is tan x here, this solid line, and its derivative is this line here. And again, the derivative is going to be asymptotic. So if we see here, we've got this inflection point here with tan, and notice that that's not a stationary point of inflection because the gradient there is equal to 1. Okay. Now, what happens here? We've got, as it approaches here, we've got a positive gradient all the way through. So positive gradient all the way through. So notice that f dash x is always above the x-axis here, or in the positive y values. And what happens here is the gradient is at its smallest at this point here, and then just starts increasing again. So at its smallest here, and then increases again at its smallest here, but we get an increasing gradient here. So we get this graph. And what it will do is repeat over and over again. And this is one of the few times in this course where I'll say, trust me, this is the case. So what happens is f of x equals tan x, then f dash x is in fact 1 over cosine x all squared. Okay, you're just going to have to trust me on this, that this function here is its derivative. Okay, and what we call it, f dash x, or 1 over cosine x all squared, we call that sec x squared, or the secant x all squared. Okay, so furthermore, that chain rule will again show that if I've got this and do a u substitution, then I end up with this as a result. And this is the one that's on the formula sheet. Now, I'm not trying to shortchange you here at all, girls, by trying to avoid to teach something that I don't really know how to do or that I'm not comfortable with. It's just the fact that you don't need to know this. All you need to do is use the rule. I'm disappointed to say that. I'm disappointed that it's kind of in the course, but it's just going to be a rule that you just have to know. All right, so let's do some derivatives. Okay, so we've got our first one here, y equals sine 2 theta. Okay, so the way I'm going to do it is try to just avoid using the rule so far, and I'm just going to try and do this using the chain rule. So I'm going to say that y equals the sine of u, where u is equal to 2 theta. All right, dy du equals, now the derivative of sine is cosine, and du d theta, that's not really comfortable to say, is equal to 2. All right, so to get dy d theta, which that's the variable in this case, it's equal to those two multiplied together, which is 2 cosine u with the u substitution, which is 2 theta, okay? And again, hopefully that's okay with the rule, but yeah. All right, now what we've got here, we're going to do this, which is actually y equals sine 2 theta all squared, okay? So in this case here, what we're going to do is kind of like a double chain rule. This is chain rule, okay? So the way I'm going to do it is y equals u squared, where u equals the sine of 2 theta. Excuse me. So let's get dy du, that equals 2u. And this one here, du d theta, in fact is this, it's what we just differentiated over here, okay? So that's going to be 2 cosine 2 theta. All right, so again, what we're going to do is multiply these two together and do a u substitution at the same time. So dy d theta is in fact this, okay, this thing here. So it's 2 cosine 2 theta multiplied by this thing here, which is 2 with a u substitution, sine 2 theta. That, after cleaning up, is going to be 4 cosine 2 theta sine 2 theta. All right. So looking a little bit uglier there, but that's okay. Let's just check that out on the calculator. Define f of x equals bracket sine 2x all squared. So note the syntax on the calculator, and we're going to go ahead and diff it, and we get that cosine 2x multiplied by sine 2x multiplied by 4. Looking good so far. All right, find the derivative of the following with respect to theta. Rarely do I get theta. I've pinched these examples of Mr. Tench here, and he's used theta here. Don't love it, but anyway. All right, so I've got this. I'm going to rewrite it as y equals sine 2 theta plus 1 all squared, okay? So important to, I like to make this move just so that I can see the function in the function and all that. So I've got y equals u squared, where u is equal to sine of 2 theta plus 1. All right, so what would this derivative be equal to here, du d theta? Well, what it's going to be is sine 2 theta plus 1, oops, where u is equal to 2 theta plus 1, and that is our u sub, okay? Derivative of sine is dy du is equal to cosine of u. This one here is equal to, oopsie, is equal to, so that's du d theta is equal to 2 in this case. So our derivative is going to be 2 cosine with the u sub, which is 2 theta plus 1. All right, so many of you probably won't have to do that move. I tend not to do that move, but it helps you understand how this derivative is obtained. Now, let's get this one, dy du equals 2u. Okay, so what we're going to do is multiply these together. So I just need a little bit more room here to write my derivative. Dy d theta equals. Okay, so it is that multiplied by that. So I'm going to get 4 cosine 2 theta plus 1 multiplied by the u, which is this one here, sine 2 theta plus 1. Okay, so there's my derivative there. Okay, so probably not enough working out space on the page there, and this is a really conservative way of getting the derivative for this one here, but don't be embarrassed if you have to do that, that's all good. All right, after doing a unit on this and after you study for exams, you'll be able to slam that derivative a lot better than that. But the chain rule is there for you to do it, just in case you have a mental blank and think, oh my God, how do I derive that one? All right, here we go with this one. Y equals cosine of 4 theta plus 1 all cubed. All right, so let's do the u sub. Y equals u to the 3, where u is equal to cosine 4 theta plus 1. All right, dy du is equal to 3u squared, and du d theta is equal to, so what we're going to have here is after the u sub, we're going to have 4 is going to come out the front. The derivative of cosine is sine, so it's going to be negative sine 4 theta plus 1. Check your formula sheet for that one there if you're not too sure how I've made that move, or feel free to pause the video and bang that into a chain rule like we did with this one here, just to confirm that its derivative is this one here. All right, now what we're going to do is multiply these two things together. So I'm going to put, I'm going to do 3 times 4, which is 12. I'm going to say that dy d theta is equal to negative 12. Now let's do our u sub. So that's u, that's cosine squared 4 theta plus 1 sine of 4 theta plus 1. So it's that multiplied by that, complete with the u substitution. All right, feel free to try that one on the calculator. So I'm going to define f of x equals brackets cosine 4x plus 1 all cubed, and let's diff it. Negative 12 cosine 4x plus 1 all squared. Note the difference in notation here. I've written kind of the notation as it's often written. You can write it like that, so don't be thinking you have to put the squared sign there. In fact, I really don't like doing that. Sine 4x plus 1, we're in business. All right, so the last couple of questions I think are looking at tan. All right, so y equals tan of u equals 3 theta. All right, so dy du equals, now what is the derivative of tan? Let's go back and review it, okay? Because again, this is one of the things in the formula sheet that I'm just going to have to note, okay? So the derivative of tan is the secant x all squared, or secant x squared. No, I shouldn't say it like that. Secant x all squared. So what I'm going to note here is this tan of u is equal to secant of x all squared, but shouldn't write x there, that's got to be a u. All right, du d theta equals 3. Going to multiply these two together. So dy d theta is equal to 3 with the u substitution, theta. All right, again, let's just try that one on the calculator. So define f of x equals tan of 3x, and let's diff it. Nice little problem to have here on the calculator. I wish this went a bit smoothly. I just had to pause that. What I did was went one round of simplify on that. So I got that answer there, thought, why didn't I get that? Then I hit the simplify button and this came up, okay? Now, why is that the case, or am I correct? Okay, well, yes, this derivative is right. So let's go dy d theta equals 3 times. Now what I'm going to do is go back to my formula sheet and note that secant of x all squared can be written a little bit differently. Okay, it can be written like this. So that is exactly the same as that. We grab the a, all right, and put it in the numerator, and secant squared, or secant ax all squared, goes down there, and we change it to the cosine function. So what I can do is the same thing over here. I'm going to grab this value here. This is 3 multiplied by, and I'm going to go 1 over cosine squared 3 theta, which is equal to 3 over cosine 3 theta. Extend that vinculum out, and we've got the answer that matches the calculator. So 3 over cosine 3x all squared is exactly the same as that. Don't know why the calculator doesn't give us the secant. I feel like it has in the past, but I just can't remember why it's not going to give us this particular derivative. This is where we're just going to have to be good enough to know that that and that is the same as that. So yeah, right, let's knock over this last one here. Y equals tan of u, where u is equal to 3 theta squared plus 1. All right, let's get the derivative of tan of u. So dy du equals, did it again, secant u all squared. Now, du d theta equals 6 theta. That's it. All right, these two are going to get multiplied together. So dy d theta is equal to 6 theta multiplied by secant u with the u sub 3 plus 1. I think that's it. So you can maybe see my hesitance with tan. It's just we just don't do it that much. It doesn't often come up. So you can see hopefully through the video here I've rolled through sine and cosine. I can't remember the last time I diffed a tan on a VCAR paper. It's not to say that it's not going to happen, but I'm just not that familiar with doing it. Okay, all right. Let's guess what the calculator is going to do. I think it's going to have an answer of 6 theta over cosine squared 3 theta squared plus 1. I think that's going to be the calculator's answer. All right, so let's do that to finish this lesson off. Define f of x equals the tan of 3x squared plus 1, just in case, if f of x, simp please, 6 theta, looking good. All right, so there's differentiation of sine, cosine, and tangent. Not that bad, hopefully. Okay, there's some practice. So jumping over to 9i and some good drill work there, along with some VCAR questions that will invariably be posted on Firefly. Good luck with it.